Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Great. Welcome. I'd like to introduce Jakob Kornerup, who's here to talk about LabVIEW, graphical programming language and interface from National Instruments. Jakob and I went to graduate school, I don't know, a few hundred years ago.
A long time ago.
And it's good to see him again. He and his team, David and Duncan, are here also from National Instruments, and they're going to be here all day today and tomorrow morning. So if you'd like to meet with them to discuss anything you see in the talk or things that you'd like to discuss with them, other topics they're interested in, please get in touch with me. And now I'll let Jakob talk.
Thank you, Mike. So I'll be talking about LabVIEW, but also be talking specifically about how we have integrated time into the language and the environment, because it turns out that time is a very important part of many of our customers' applications. So it's an essential thing for us to integrate. Let me first talk a little bit about who we are. We consider ourselves to be leaders in the computer-based measurement and automation, basically in doing activities where customers need to bring physical signals into a computer and do something with those physical signals. We've been around since 1976. We're based in Austin, Texas, and we are fairly worldwide coverage now in terms of employees. So, one key thing about what we do is that we have a very integrated perspective on the role of software and the role of hardware. And we really see that it's a combination of software and hardware that makes our customers successful. It is not just software, it's not just hardware products, but it's the ability to put the hardware and software together in such a way that they are able to, again, take these physical signals and bring them into the computer and do something with them. And that's what an important part of that interacting with the physical world is the understanding of timing. So I'll basically base my talk around the concept of timing and see how it shows up in LabVIEW, and also starting out by motivating a little bit of the timing, and then talk about how time actually plays an essential role in taking measurements. And then the bulk of the talk will be on actually how we've integrated time into the language, and I'll show in different aspects how we've done that. And I'll end up with talking on some work we're doing on formal verification of LabVIEW programs, and also about the timing of those programs. But let me start with a motivating example here. This is kind of a stylized picture of the Western Electric power grid. And this is basically where you get your power from out here. And this is an actual measurement at the Malin Mountain Station on August 10th, 1996. And here we can see the output from this in megawatts here. We can see how things start oscillating. And then at this point here, we have the blackout. And I don't know if many of you were actually here on the West Coast at that time, but this was a significant outage, estimated cost of several $1 billion in actual cost to the economy to recover from this blackout here. And the challenge is, of course, what can you do with this? So this is data that was recorded, actual data from it. The problem was, how do you prevent this scenario from happening? And you can see the good thing here is that there's actually some 70 to 80 seconds from the first instability starts being introduced here in the power grid till the actual blackout occurred. So there's actually time to make corrective measures here. The problem is, what are the corrective measures? How do you do that? And we have a customer of ours who's actually working on getting this, solving the problem here so that the system can be stabilized. And the way they're doing this is by having sensors placed all around the grid to give input, to register the output at each of the substations that are part of the grid, and then using GPS synchronization to align the measurements that are being taken across the grid here so they can actually be compared. Because if you can't compare the measurements, you can't do any meaningful correction to it, because you don't know where you get a lot of graphs that look like this graph here laid on top of each other, but if you don't know actually what's happening at any point in time, you can't make corrective action. So they're using the GPS synchronization to take these measurements, bringing it into a central site, and then, based on that, they're able to inject stabilization back into the system to avoid these type of instabilities in the system. Of course, it's a very complicated control problem, but from our perspective, the essence of the measurement here is that these measurements have to be synchronized. And this is, of course, over a very wide area, and this is why they're using GPS for synchronization. So this is just one example of how timing plays a role in a very concrete way that, and basically enables them to build a stabilization system for the power grid. So these are some of the things you have to consider when you're looking at a measurement system. You have to think about how you're sampling, what's kind of triggering that's going on. For instance, in the GPS example, they're using the pulse per second as the triggering for their acquisition, so that's how they get them aligned. Looking at stimulus response measurements, and also these global triggers and clocks for synchronization. And then some movements of data, how you actually move the data between the acquisition device and into the computer, and how the computer actually gets notified that data has become available. And here are some. Here we have a time scale of from nanoseconds all the way down to milliseconds of different technologies that can be used here. And also, we can kind of see they shift from being purely hardware over to software. So we start out with some backplane timing technologies that allow you to get very precise in the sub-nanosecond range synchronization between your devices. And then you can get I/O synchronization using a global clock. You can then start introducing software-programmed FPGAs where you're kind of going from the hardware into the software. And now we're going to go into some time loops, and I'll explain those later, what they are in terms of programming your applications with these timing constructs. And then going more and more into the software world where you get looser control of your timing, but you get more flexibility in your application. So these are some of the technologies that are available. Another way to look at the timings is that this is some of the technologies that we have actually done for timing. On the top side, we have a lot of hardware technologies. On the bottom, we have a lot of software technologies that are available that we have made available to our customers. I don't want you to read this thing here. I'll point some of them out as we go along. But I just want to point out that this is actually some things we've done over the 30 years or so we've been in business, basically introducing these timing technologies as they become relevant and available for our customers. But this here is a general slide here on some of the synchronization technologies that are available. So here we have the precision of the synchronization going all the way from picoseconds down to seconds here. And this is something about the distance between the devices that are available to you. And the first class of synchronization technologies are what you can call signal-based, where you have physical signals propagating between the entities in your system. So you may have actually on-chip connections between pieces on your device. You may have backplanes. We have some technology called PXI that's derived from the PCI platform. We also have an ability to go across multiple chassis. And there's an interesting line here coming down. That's basically the speed of light here, the propagation of physical signals. There's a limit to how fast you can actually synchronize when you go over a distance. And it turns out there's another category here, which is time-based, where you're exchanging messages between the devices here. So you're no longer propagating a physical signal, but you're exchanging information about what time it is, and you're using that to synchronize the clocks on either end. And there are some technologies like, for instance, the GPS or IRIC, but also an emerging technology called 1588 that allows you to get highly precise synchronization over Ethernet. So there you can get into the nanosecond synchronization using standard Ethernet technology. But what you're getting here is a time-based. You're getting synchronized clocks. You're not necessarily getting a physical pulse train that is being distributed between the devices. Here's an example of one of our customers, that's Boeing, that is using some of these synchronization technologies for measuring the noise that is being emitted from different airplane designs, and basically retrofits to this. I believe this is 737. That they're looking at the airframe noise and the inlet noise of the aircraft. And what they're doing is they're flying this over an airfield, and they have 8 what we call PXI chassis, which are just computers that are synchronized with each other, so that these measurements again can be correlated. And they are then hooked up to a very intricate array of 448 microphones arranged in a very special spiral pattern to basically capture the entire sound from this over this wide area. I believe it's like 250 by 300 feet, this area right here that they're covering. And these are actual measurements that they've taken from an aircraft to show where the hotspots are for noise, and to look at what they could maybe do to optimize the design. So this is where they need this tight synchronization over some distance to be able to, again, correlate the measurements from the different microphones. And they're able to get within 1 degree of precision of these measurements for the aircraft. So this is a very typical example of what our customers are doing with timing on the hardware side to basically get precise measurements. What I'll now move into is talking about how we can deal with time and concurrency in our software. And I'm actually going to start with a little quote from one of you guys. Basically, the concurrency revolution is likely to be more disruptive than the OO revolution. And this is something that we've also become very aware of, and something we actually feel that we have some very good answers for. And I'll show you that in a little bit. But this leads me up to talking about the primary thing that I work on, which is the LabVIEW programming environment. So LabVIEW as a base is a graphical programming, data flow programming language. We call it G, just to give it an acronym. It was invented around 1985 by one of our co-founders. And what it is an integrated program development environment with an editor, compiler, linker, debugger, multi-platform, runs Windows, Linux, and Mac, and multi-processor architectures. But at its core, it is a programming. The programming idea here is that there is what we call a block diagram, which is this data flow visual representation of your program in conjunction with a graphical user interface where you can see exactly what's going on in your application. So you can put down these connections between what's happening in your program and the visual part of it. And these two things always come hand in hand. They come as a pair. So you always have a graphical interface to your program. So you can easily see the output of your data. You can easily stimulate your program for unit testing to basically see what's going on. And that's the graphical part of the graphical aspect is that it's not just a textual way of programming, but actually you're using graphics for input and output as well as programming. It has a strong way of integrating with C libraries. We also have extra ways of integrating with .NET assemblies as well. And at the base of this is a large library of signal processing, which is really at the core of our customers' needs, is to be able to process these signals that they acquire from the real world. By the way, if there's any questions here, please ask, and then we can, if there's anything you want to. Come on, absolutely.
We also run on 2 RTOSes.
That's right.
One proprietary and one commercial.
Yeah. And I'll actually get to that in a little bit as well.
Quick question.
Absolutely.
Do you sell G as well, LabVIEW?
We sell that. Yeah, LabVIEW is a commercial product. Yeah, you can go buy it. So let's look a little bit more at the G graphical programming language. So it's a homogeneous structured data flow model, and it's a statically typed model. So let's look at a simple program here. I've kind of taken some pieces of it, but here we have 4 constants, and we have 3 adders that basically add together these values here. And then this is a connection to the front panel that will show this value on the front panel, the graphical user interface of the program. So this works by data flow, basically, that each of these nodes will execute when this data is available to it and then produce an output. So this node has to wait for these 2 nodes to execute. But the nice thing here is that these 2 pluses here can execute in parallel. There's no order specified on how they have to execute. So that's the base model of computation here. Now, what we add to that is we add structures around this base model of data flow here that allow you to do more things. And I'll show you that in a second here. So here's a very well-known program, Euclid's algorithm for computing the greatest common divisor. And what I have here is, again, a base data flow graph inside a structure. This structure here is what we call a while loop. And think of it very much like a while loop in any imperative programming language. It has a condition, which is this stop symbol here. When that evaluates to true, the loop will stop iterating. It has provided some inputs over here. And then once the inputs are available, it will start evaluating the data flow graph on the inside. In this case, it will take 2 values in. This is a little symbol that takes 2 values in, returns the maximum on the top and the minimum on the bottom. And then it computes the difference here with this primitive right here, and compares the 2 values for equality here. And if they're equal, it'll stop. These nodes here on the border are a little special because what they do is they keep the state of the while loop, meaning that when the value comes here, it is then propagated over here to the next iteration of the while loop. So this is the only state holding element in some sense of this structure, is the shift register right here. And that allows us to pass state from iteration to iteration. And then once the stop condition evaluates to true, the value here, it gets propagated out and will be put on the front panel. So this is a simple example of a LabVIEW program that computes the greatest common divisor. It's just written a little differently than in a textual language. Any questions on GCD? Okay. So as David mentioned here, LabVIEW runs on a whole bunch of platforms, starting off from the more standard PCs, but going into the real-time control space as well, where we have these more industrialized, ruggedized formats, but also going into handhelds and FPGAs, and even into the Lego Mindstorms. That's actually I don't know how many of you are aware of the Lego Mindstorm products, but that's actually a LabVIEW programming environment that is in there. The user interface is a little different on it, but it is LabVIEW in its essence. So basically, we're covering a wide variety with one programming language and one programming environment. And one of the things that is because of this inherent parallelism that is easily expressible in LabVIEW, it is possible to take a computation like this one here and basically map each sub-computation onto multiple threads and then have them run in parallel before the result is actually being returned. And this has been inherent in LabVIEW since 1998, the ability to run on multiple threads and run in parallel and take advantage of multi-core and SMP type systems here. And the nice thing here is that the user doesn't really have to do anything in terms of being explicit about this mapping here. They just have to write code, and the data flow dependencies will basically tell the compiler, or the compiler will basically find the data flow dependencies in there and schedule according to those. Okay, so the bulk of this talk is going to be on timing. How do you program the time here? Because what I've shown you now is just the data flow, the pure data flow model of LabVIEW. But what I've actually worked on at National Instruments is trying to figure out how to get time into it. Because it turns out that time and data flow are very orthogonal concepts, where the data flow model, as I showed you, is purely about nodes that execute when data is available to it, but has no concept of what time it needs to execute. So what we introduced some years ago now is the time loop construct. This is one of those structures in LabVIEW that allow you to organize a data flow graph on the inside, but specify the timing of when this structure has to execute. Again, this is an orthogonal concept to the data flow, meaning that this is a structure in LabVIEW. It will only execute when all its inputs are available, according to data flow. But we put the further restriction on that it has to obey the timing specification you give to it. And each iteration of this loop also has to obey the timing specification you give to it. So in this case here, we say that every 1,000 ticks of the underlying timing source that is defined for this structure, this loop should execute. And what you specify with it is, where does time come from? And this turns out to be something that's important for our domain, because it is not just, time is not just milliseconds or ticks of a CPU. It can be the time that's coming out of the actual physical environment that's being measured or controlled. Think of an engine, for instance, that is a rotating engine where you have an encoder that is telling you where the engine is in its rotational position, 360 degrees all the way around. That is, in some sense, you can think of that as being a time base that a program can run by. And it needs to do certain things when the engine is at a certain position. And that depends on the speed of the engine, basically how fast it is rotating. In other words, you can't correlate that to a simple millisecond, microsecond timing, because it is all dependent on the rotational speed of the engine. So that's what you can specify out here. You can specify other sources of time besides just this inherent computer time that is relevant to the measurement you're taking. And you can then use that to run your data flow graph based on that timing. And we actually have some ways for you to overlay the two types of timing domains so that you can use both in your program if you have application. There are, for example, examples. in engine control where because of spark plug warm-ups that you have to do things that the warm-up actually takes a certain number of microseconds, but the rotation of the engine is still determined by this encoder signal that's coming in. So you need both elements of timing in here. So what you do here with this structure is you program your timing. You say, when does this need to run? And then while the structure is running, you can get a lot of information about what is happening time-wise as this structure is executing here, and as the timing source is actually running. And you can use that in your program to adjust or report back on the results of execution. And you can even use that to change how it executes at runtime. So you can dynamically update the execution of this structure at runtime. And then finally, when the structure has finished executing, you can get some statistics out on how it actually behaved while it was running. The idea here is to give the users an abstraction of what they think of when they program real-time control systems, which is a task. The idea of, I have this task, it has a certain frequency it needs to run at, and I need to record certain things about how it's behaving. I need to read my I/O at certain points, and I need to be able to output data at certain points in time. So time has now become an essential part of the language by giving you the ability to express behavior over time in conjunction with the data flow. So any questions? Yeah.
Do you have data flow operators that are allowed to actually read the time and make decisions based on what time it is or how much?
Yes, that's what these here do in some sense. Now, you can do that on this boundary here, because this is when the data flow interfaces with time is when the structure starts, for instance. So here you can actually say, read the actual start. You know exactly when this was started to do, because this is all, when this is running in a real-time system, you may have specified that this had to start at time 100, but it may be time maybe 120 when it actually starts running. And at that point, you now get to know when it actually started. So you can make decisions based on that.
There are specific primitives for querying time independent of the boundary structure.
Yes, that's also independent. Yeah.
Data flow structure that's triggered by some non-periodic random event, and then strict timing after that, but using data flow, you can do that.
So let me just take a simple multi-rate example here. We have one loop that runs every 1 millisecond and takes 300 microseconds to execute. And another loop that runs every 100 microseconds and takes 50 microseconds to execute here. So we basically have blocks of A's here that are spaced millisecond apart, and we have these B's here that are spaced 100 microseconds apart here. And the challenge is that if you start running an A here and will not allow A to yield, you're going to have all these B's basically be late. So if you're not, basically if you take a very naive approach to scheduling this here and just say that the A's, let the A's run, then you're not going to be able to basically fit the B's in. Or vice versa, if you just say B's will have to run, then the A's will never really get to run, because so what you need to do is you need to be able to interleave the execution of A's and B's. And the way you can do that is by using a standard technique in real-time systems called rate monotonic scheduling, where the one with the fastest rate gets the highest priority. So you basically say B has to have a higher priority than A, and B will run whenever it needs to, and then A will have to yield. And you end up with an execution that looks like this, where you basically chop the A up into little pieces that run when the B is not available. And we can see that both of them can then fit into the timeline here. And all you need to do here is associate a priority for A that's lower than the priority for B. And the way you specify that in the time loop is just you basically program your A's and your B's, and you give them different priorities. So this is the A that has the priority 100, and this has priority 101. So you can explicitly state the priority. So this leads to one particular way of scheduling based on priority here, and that's the one we currently have implemented here. It doesn't mean that so that's at the core of it, because it maps nicely onto many of the real-time operating systems, including the ones we use, this notion of priority-based scheduling. So that's how you realize the example here with the two loops here. And one of the things we actually visualize that this is a tool we ship with our real-time system, that you can actually see what happened in the system. So here we have what's happening in thread A, in time loop A, and here's what's happening in time loop B. And we can see that B gets to run first, and then A runs, and then B runs, and so on. So we can see that that graph that I showed is actually what happens in the real-time system as it's running. So this is a very, very nice tool for after the fact looking in to see what happened in your real-time system, and if you have any anomalies, to debug those anomalies in the system. So how does this work here? And this is a little bit goofy, but basically what we have is we have a scheduler sitting in the middle here that decides based on the different timing sources. Remember, time is not just what's coming from a CPU tick or from a timer, but it can also be what comes from a data acquisition device. These kinds of signals that come in. It determines then what is the next things that need to fire and then wake up the different time loops depending on what is the next thing that needs to schedule. And it actually has the ability to schedule based on these different timing sources simultaneously. Okay. Then the latest thing we've introduced is the ability to schedule these time loops on different cores. Because with the advent of multi-cores, we found that the ability to run real-time systems on multiple cores is very, very important. So here we have an example where we have a time-critical control loop that you can assign to one core. And then you can move the non-time-critical aspects of your application over onto another core. So basically you get a separation of the time-critical aspects and basically devote a core completely to your control aspects and then move many of the normal priority activities over onto the second core. And you do that by explicit mapping of to the cores. We also have a way for you to basically let the system try to load balance things on the cores, but that will not necessarily give you the same determinism as you get here with explicit mapping onto the cores. But what we have here is actually running on real-time systems on SMPs with very high performance results. And one of the so this is just a way for you to visualize what's happening here. It gets a little difficult when you have multiple cores to see, but here we actually have the ability to see both the activity on both cores. Here we've highlighted what's happening on one of the CPUs, and the other one kind of fades in the background, so you can again debug what's going on. And here's an example of one of our customers using this. This is at the Max Planck Institute in Germany. They're looking at building a tokamak, which is one of these plasma reactors. And they're basically using magnetic force to keep the plasma in place. And Luigi Arnon is one of the scientists on this here. And he got very excited when he was able to start using LabVIEW real-time with this SMP solution. And I have to take this with a little bit of grain of salt, but he says with LabVIEW we obtained a 20x processing speed up on an octal core processor. Really what this means is that he actually, with one core, he couldn't get the job done, what he was trying to do. But then, because it was just too slow. But once he got a multiple core system in, he actually started saying, oh, I can get this done. And not only can I get this done, but I can do it better and better and better. And that's actually where he got to the 20 times speed up. The point is that he was able to get to being able to solve his control problem for the plasma. And this is a hard control problem here. It involves multiplying very large matrices in real time to do the control of the plasma. And that was the thing that he couldn't do on a single core system. So, so this is an example of how that's being used. Any questions on multi-core? Okay, let me move on then and talk about time triggering. So this is another. So this is the kind of the third thing about timing I want to talk about. So this is a time trigger network that we have introduced some years ago for doing deterministic communication over Ethernet. There's really nothing particular about the networking technology, but what it does allow you to do is deterministically share data across a dedicated Ethernet network among real-time systems. And with using software, we're getting about 5 microseconds precision of the clocks on these devices here. And what you're doing with this network is you're scheduling all the traffic that goes on between the real-time nodes, so that it is determined ahead of time when these communications are happening. And that's very similar to a number of off-the-shelf technologies like the ones at the bottom here. The way you do this is by defining your network. You set up what is the period of my network. This is given in microseconds here. You specify exactly when should the different variables be transmitted. So here are some variables here that are being transmitted across the network between these real-time targets. So in this case here, we're going to be looking at a hardware in the loop simulation. I'll show you that in a second, how it works. But you specify this timeline, and then you specify exactly when these communications happen on the network. And what you get here is, out of that, you get these timing sources. And this goes back to the time loop that I talked about earlier. This allows you now to wake up your real-time activity, your real-time loops when these things are happening in the system. So you can actually specifically say, I want the loop to wake up at that point. The example we're going to look at is where you have a model of an automotive engine and a model of the electronic control unit for that engine. And you're going to be basically communicating different parameters between these two models, the RPMs and the throttle of the engine, and then the timing and the fueling going back to the model here. So you're basically going to have these two entities communicate with each other. Now, you'll see in a second why that's done over a network. So you have these two models running here. Because at some point you may actually want to say, rather than just a model of the ECU, you may actually want to have an ECU you're in the process of building. You may actually want to put that into your system here. The model of the engine doesn't know any better. It's still seeing something on the other side that looks like an ECU controlling it. But now you're actually testing out this ECU, but you're testing it out against a model instead of a real engine. And if there's any bugs in this, you're not going to have a crankshaft and cams flying left and right because you're not controlling it correctly. You're just seeing it in the model here that is behaving out of whack. So that's a very common technique being used in many product designs, is to use this idea of hardware-in-the-loop simulation. And turns out that the network actually provides a very nice interface between these two components here. So here is a layout of how you can communicate the variables between this. So we're going to get some values coming out of the ECU and some values coming out of the engine here and be communicated between the systems. Absolutely. They do. This is the programming tool. They lay out the network. It's statically scheduled when they communicate. They specify when the communication should repeat. They specify the timing sources up here, when they want the different things to be for the programming, when they want the loops to be woken up. Absolutely. It is, exactly. It is depending on how big the data chunks are. And it's basically calculated on some of the line speed of the network with some padding on it, so it can be done. It's automatic done, yeah. They just say, I want to transmit a variable of this size. In this case, it's actually just an array of doubles here. Question?
When you bring these other hardware pieces into the loop, how do you maintain a global time base amongst them, so that actually when you say the message should happen at some time, it's the same time to affect all of the...
You still have an interface there that becomes a question of now interfacing the ECU with the timing model you have in there, and that's up to how the timing from that ECU, how you're actually able to interpret that in your software, in your hardware components on that side, and that's still something that depends a lot on how you set it up, how that can be done correctly.
So you have to make the instrument the ECU stuff.
Yes.
An additional manual programming task where you use, say, the DAC API, those little cards we have to do visualization, to observe something about the ECU that gives you a time base.
That's right.
And then you wire that into the timing source.
That's right.
But correlating the existing system behavior when there's two network simulated entities to when one simulated entity goes away and it's real, that's still a hand-rub job.
It is not just as easy as I just put, but the point is that you can do that. There's a mapping way of doing this. So, okay. So that's how you specify it, and now you start programming. So here you write a loop here that models the engine. So here we have, when it gets a value coming in from basically the timing source that drives this loop is the reception of the value from the ECU. And then it reads, so in each iteration it will read those values from the ECU. It will run a step of the engine model and then send the values out to the engine. These are variables, which is a concept we use in LabVIEW to communicate either between concurrently running loops or between distributed applications. So basically, in fact, I think I have some animation that shows this. So the values here basically cross here. So this value that's being written here will then be available in the next iteration down here and vice versa over here. As data. Exactly. And in fact, here are not even on the same computer. Yeah.
But why, since it's triggered by the arrival of value, why isn't it just put into its block diagram? I don't understand why it has to come out of the loop.
You're talking about this one here?
Yeah.
Because this configures this loop to say the timing that runs this loop is based on that.
But why not use the arrival of the value anyway? That way the data flow will be more explicit, right? Rather than coming out of the...
Right. So you're saying this could be blocking on that?
No, it could be, you could move that out of the box and say this is, whenever this
Right, but the thing is that this is a loop. Actually, it stays in here and it keeps iterating in here. So that's how. So this is a looping structure. You stay on the inside basically until there's an error.
I was asking, so if you're looping and it's time to do the loop again, if there's not a fresh value for that TT ECU out, it's going to operate with a stale value.
No, it's going to wait until the next one that comes in.
Which is his point. So we could have had the input to the loop be a data flow arrival similar to the event arrival and then propagate the value on. That would have been one way if we did it. There are various other reasons that we have an independent node, and they're largely not for this use case. So yeah, you could have done it that way.
You could have done that.
So far, everything was nice, but now you sort of basically adding global variables, right? This is where I'm a little worried about it. I'm just reading this global thing.
You're reading this global, but it is tightly tied.
It's so timing based.
It is.
Now the synchronization of which value we're getting when is no longer apparent in the diagram.
Right. From a representation point of view,
You're right. You're right.
What if you had that little orange box in two different places in the same loop? Is that possible?
That is possible, yes. Because here, all you're doing here is reading a local copy of that value. You're not actually waiting for anything to come in at that point. These are non-blocking reads of local copies of these values. It is the fact that that the loop gets triggered on the arrival of that means that you have fresh data available to you.
your question and your question both get to areas that I think we still spend and are spending a lot of time, which is we had the data flow representation nailed. That's the comfort level. We've been doing it for a while. It's when you have essentially asynchronous actors that are passing data outside the bounds of data flow, whether it's a time or event-based passing. How do you represent those data exchange policies between whether they're processes or tasks or whatever? And your two-node question gets to, if the first node fires, is that going to read one value, and the next node fires, is it going to read a different value, or are they have their own private buffers of never missing an event? And those are all different models of doing data exchange. We haven't formalized them all. We're pretty close, I think.
One notation we use in at least some cases is being able to grow that node and have multiple variables listed there, and that at least indicates a logical these things must be
Simultaneously.
The relationship of that, the enclosing structure that you hinted at, is something that's still
And I actually have
not really known down.
I have a slide on some other ways of representing similar things to this, not exactly this application here.
We do also, we have cases where we want the synchronization to occur on a value change. We also have cases where we do want to read stale values.
Yes.
Where we literally want to say, this thing always runs this off, and go with whatever you got. That's more common in industrial control.
Yes.
type scenarios.
That's right. That's right. And by the way, these are communicated because of the networking. They are communicated with fixed intervals between them. So it gives you that pattern of time, of repetitive time. It is not that these are just asynchronously arriving data. It would be very different if you did that based on that. Okay, and then of course at the end you can basically swap out the model from the interface of the real issue. And of course that is just a sleight of hand because as I said there's much more to it than that. But in essence that's all there is to it, to replacing it here. And what basically the design philosophy here is that in the programming world, we're trying to abstract away a number of these very intricate aspects of the hardware architecture. Let's go back to the diagram here. This is fairly high abstraction for programming time-trigger network, programming things with a distributed real-time system here. But the idea is you're actually expressing the things you care about. You care about the arrival of data. You care about reading the data because that's in essence what the model needs. But you're trying to separate these things out from the more details of what particular hardware architecture you're running on, what is exactly the data transfer mechanism here, and many of the aspects of the hardware-software boundary. There's no notion of operating system in that application there. It is just plugged in, and this goes back to where our customers are coming from. Many of our customers are not computer scientists. They are scientists or mechanical engineers, aerospace engineers, and they are not very well versed in writing interrupt service routines, which could be another way to do this on, but it's just dropping down to a completely different level of abstraction. The idea is to lift it up here so they can work at these higher level of abstractions, but still get the performance they need. So one of the things I skipped over is that this is fairly high speed. We can actually close a control loop around 5 kilohertz on an Ethernet network. So in a deterministic fashion. So I mean, it's reasonable performance you get out of this here for building systems. but doing it at a high level of abstraction. Another thing that also this networking aspect gives you is temporal isolation. We have some customers that are basically building different aspects of a system, and they where each component is delivered by a subcontractor. And if you're building a real-time system, that's one of the hardest things to do by contract, because not only do you need to get your functionality right, but you also need to get your timing right. And if you're building around this model here of a time-triggered network, each vendor can then get its own allocated slot on the network. And if their system cannot meet the deadlines, the data doesn't get in time, well, it's very easy to analyze, and they cannot step over the bounds of what the other components is. So you end up avoiding some of the finger pointing that you otherwise get if you're trying to integrate a real-time system on a single machine, by actually having this rigid separation by time and having the network arbitrate the schedule for them. Okay. So the last LabVIEW aspect I'll talk about here is the FPGA programming. So we have a module of LabVIEW that basically takes the same type of diagrams that you write and then compile them down and run on an FPGA here. And this is a very powerful and very an area we're seeing a lot of growth and interest in, because again, this is the programming model. But what it allows our customers to do is now define a hardware circuit that will, in our case, is always talking to I/O, that allows them again to bring the data into this FPGA and do their program, their transformations and their analysis of the data inside the FPGA. Doing it at the speed of the FPGA, which is very high, and doing it with the determinism and the parallelism that's available in the FPGA. So here we have these 4 loops running on the FPGA. And basically, you have as much parallelism as you have basically space on the FPGA, unlike with a multi-core where you're fixed by the number of cores on your system. So it's a very, very powerful I/O processing and computing platform. So these are some of the examples of what our customers are using. One of the things, for instance, they're doing a lot is digital communication protocols. There's a whole bunch of these protocols where different signals are propagating along serial lines, and where people are basically have to extract the information in a certain way. And these FPGAs turn out to be very, very efficient for processing these type of protocols. And it's very easy to write those applications in LabVIEW. But there's other examples as well. And these are some of the platforms. This is probably the most interesting one I think we have. It's a very, very small form factor, very ruggedized platform that has a real-time processor and has an FPGA on the backplane, and then has these different I/O modules you can slide in and basically get the measurement type that you need to do in your application. You program the FPGA in the backplane to do the first order of signal analysis and signal processing, and then you can move the data up to the real-time processors of a further floating point type of operations on there. And then you can communicate data out through Ethernet up to an operator interface as well if you need to do that. But basically, it gives you a very, very complete way of programming real-time systems where you can take advantage of the FPGA and the real-time process depending on what you need to do. And you get a lot of flexibility using this. But we also have other things that are more plug-in boards for PCs as well, where you can program the FPGA as well. Again, with I/O right by the FPGA. One example where this is being used is the Large Hadron Collider at CERN. Here they are using our FPGA board products for controlling the beam in this experiment. I don't know how many of you are aware of this, but this is one of the largest instruments that's ever been built. And the beam is about this long, about the width of a hair. But it has enough energy in it to melt a ton of copper. So basically controlling this thing is essential. And that's what they're using the LabVIEW FPGA with motion control to make sure the beam stays in place. Or if the beam actually goes astray, which sometimes happens, they have a control way to divert it into a tunnel and then basically have it hit a big slab of concrete. So I can.
Geneva Airport.
Sorry, yes, it does. Yes, it's a 27-kilometer ring that's out here, and they're using some. I think it's 110 or so basically stations along the ring to control this beam here. So it's an extremely large, of course, operation here. And but they basically, and timing is everything in this here. The fine control of each individual collimator, but also the synchronization that has to happen because it's around this big ring here. And they have some very interesting synchronization technologies that they're taking advantage of there.
This happens case where formal verification might be particularly interesting.
Yes. Unfortunately, they're going live next year, and we don't quite have formal verification yet. But that's probably a good segue to me to. I'll almost get there to talk about that. One of the things they're using on the FPGA is a variation of the time loop that is what we call a single cycle loop, which is basically allows you to take a diagram that's in here and run it within a single cycle of the FPGA, and basically treating the data flow graph here as a combinatorial piece of logic that can then run at that rate here. So it's basically a way for you to specify timing, but at the level of the clock now of the FPGA. Also, I just want to show that quick down here. We have this is our continuous time simulation diagram that works with simulated time and allows you to do continuous time simulation. We can actually also run in a mode where you hook it up directly to hardware, so you actually hook it into the hardware timing as well if you want to do that. Question?
If you have those clock switches faster, are you saying the FPGA clock or for the external one?
For the FPGA? Sorry?
You're doing many cycles inside a larger cycle. Which is larger, which is smaller?
You are basically doing, okay. So this is a looping structure, right? And it basically runs at the base clock that you designated for it. It can either be the 40 megahertz base clock that we have on there, or it can actually be one of those the derived clocks that you have on there that can be multiplied up to some top speed of it. So I don't know if you I don't know what.
In a large majority of use cases today, the clock on the FPGA itself runs faster than the I/O phenomena you're trying to monitor, and that's actually a good thing. So. In terms of clock rates, in general, it's faster than the external clocks that we would have used in a non-FPGA-based model. Not always true, but in a lot of use cases it is true. And what that really allows for is, it's not accounted for here, and people who don't do I/O wouldn't really care. But essentially, if the observer of the phenomena is running faster than the phenomena itself, you can just sample a single point. And so the complexity of the data you're dealing with is just a single scalar 9 times out of 10. When the phenomena is occurring a lot faster than your computing power, you have to introduce all of these different hardware buffering schemes and buffered time stamping and all these other things, and it introduces complexity all the way up into your programming and driver model. So what this does is run your logic a lot faster than the real world, simplify life. Kind of.
That's the basic. Yeah. Okay, so this is what I was alluding to. This is more futuristic. So this is another perspective on, well, what do we really mean about having time as a first-class citizen on the diagram? Well, here is actually an attempt of saying, well, let's have wires that can carry time on the diagram. So these are special kind of wires. These are not the wires that I've shown you before. In fact, the only wires I've shown you before are these little thin ones down here. The idea is that these green wires here are actually carrying time information. So this is coming from a digital port on some board here, and are carrying physical pulses in here into this frequency distribution device that basically where you configure it with a sample rate, and then it will produce a pulse train that is according to this sample rate here. And it will then be used to trigger, this is an analog input or ADC block here, that will basically, whenever a pulse comes in here, it will then read a physical value and put the numeric value on this wire that can then be accessed and do it for a control loop here. And similarly over here we have an analog output that will then take, when it gets a pulse, it will output the latest value that's seen here and send it out to the physical world. So it's a way for you to propagate these physical signals, specify how these physical signals should be propagated and the timing relationship between them. There's some little subtleties here that this actually happens on the rising edge of that clock pulse here, and this happens on the falling edge of this clock pulse here. The point here is that this is being very explicit about the physical signals that are flowing in your system. And these are concurrently running actors, all these nodes that are sitting here, that are receiving these signals, almost like you're designing a piece of hardware. But it is done with an abstraction that is about signals and not about electric wires. So this is one way you could represent very explicitly the timing in your application. These wires don't have to just be physical electrical pulses. They could also be things like timestamps that could be floating down the wires as well. So there's a couple of different variations of these here that can be used depending on basically on what underlying technology you have available for you. This is very well suited for FPGAs because here you are literally dealing with these rising and falling edges on wires. But in a more compute-based system, you may be more able to cope with timestamps flowing on wires. So this is some of the ideas we're pursuing in terms of being very explicit about time being a first-class citizen on a diagram, actually flowing on the wires of the diagram. Okay, last piece I'm going to talk about, there won't be a few minutes for this, but basically is formal verification. And this is something that I've been doing with Matt Kaufman down at UT's Computer Science Department. He's one of the authors of the ACL2 theorem prover on formally verifying LabVIEW programs. And what we're basically seeing, and I think it's also come out of some of the things I talked about, is that as we're moving into more and more of these hardware and control type problems, people are beginning to say, well, what about the correctness of these things I built? Now I'm building a control system. Will it actually do what I think it does? We're actually seeing people, they are getting FDA certification for some of their products, but they're not quite sure about that. Have we actually realized our specification? So we're beginning to get some feel for our customers asking for this here. And we think there's actually something in LabVIEW's graphical nature that makes it amenable for formal verification. And I'll try to show that in a little bit. So here's some very early sketches of what we're graphically going to do. And this is going to probably look a lot different when we actually start really getting into something customers can work with. But up here we have a very simple LabVIEW program that takes, this is a for loop that runs n times where n is supplied as an input. And then on each iteration, it takes the current count and adds that to this shift register here that's initialized to 0. And of course, you probably recognize this as basically the Gauss summing of the integers. And down here, we have a little theorem block that basically specifies the relationship between the inputs to this piece of program and the outputs of this program here. So think of this as being a way of asserting pre- and post conditions of a program. So this is basically saying that if the input is non-negative, that implies that the output is n times n minus 1 over 2. So basically, that's a way of stating it, but it's done in a graphical way here. So this is the statement of the assertion in the language. What we've done is we've implemented a LabVIEW to Lisp compiler. I have to say this is a small subset of LabVIEW to Lisp compiler. It basically takes these diagrams and translates them into ACL2 code. Which also has a nice benefit of now we actually have another way of interpreting LabVIEW programs within this environment here. And one way to think about, ideally you want to say that this is a theorem you would like to prove about your program. It may not always be possible to prove, of course, this theorem. First of all, it may not even be a theorem of your program. Second of all, it may just be hard to prove, no matter what tool you're using. But another mode of this, of course, is assertion. Basically, you can leave this in as an assertion in your program. So you have the duality between theorems of your program and assertions that can be checked at runtime. But if you can actually verify them, then you can remove those assertions from your code. And for instance, if you're dealing with hardware FPGAs, that means you actually can free up some space on your FPGA if you don't have to have the assertion as part of your program anymore. This has been, our project has gone through a couple of stages here. We started out not being tied to ACL2 as tightly, where we basically just use ACL2 as a tool. We would ship some certain theorems over to, but we will keep all the logic in our own little world. But we've now actually gone to a more deeper embedding into ACL2, where we basically translate the LabVIEW programs and the assertions into ACL2 formula, and then the ACL2 reason about it. And we believe there's a lot more leverage there because there's a lot of large body of work in ACL2 that we can actually take advantage of for doing this. And also we can now do co-simulation between LabVIEW and the ACL2 world, because the nice thing about ACL2 is it is applicative, so we can run it as well. So one of the things we're looking at, as I said, we just started. The type of problems we're looking at are the kind of problems I showed you here. Some very, very simple looping structures, but we're slowly moving on. With Matt has basically been on us for with us for 6 months now, working as a contractor for us, and we're getting to the point now where we can start looking at things like state, how to handle state in these systems here, and also we're going to start looking at more explicitly data types and how to model the data types. And again, this is where the ACL2 libraries for handling, there's been a lot of work done in the ACL2 community on handling data types in different ways here. And one of the tricky part for us is handle I/O. How do you actually model the I/O and actually prove properties of the I/O? One of the things I do believe here is, though, is that there are some aspects of the graphical representation of LabVIEW that makes it easier for end users to take advantage of theorem proving, because we actually have ways with graphics to overlay assertions and overlay the proof structure on top of the diagram, as opposed to in a textual thing where you have to kind of interleave it together in a more linear fashion. So I think there are some things here where we can actually can help people do it. For instance, how do you frame the invariant properties of a while loop? Well, you can actually expand the graphics of the while loop and overlay it with the aspects that you need to provide in order to prove your while loop. But still have an aspect that is just the base program, and basically have the views of these things of the two things. Let me skip over this here. The last thing I want to talk about is, of course, tying it back to the timing, is that one of the things we would like to do is we would like to prove timing properties. So this is a very simple example of an FPGA type program where you have a digital signal coming in, you have some computation taking place, and you have digital signal going out here. And you would like to be able to state something like, when the line here goes high and the clock has a certain value, well, then you get to a point where the digital outline goes low, and the clock has progressed no more than 5 ticks from that point onwards. And so, that's the linear way of basically stating what's written here in this theorem block right here. So we would like to be able to prove properties like this of the program. Of course, in order to be able to do this, you need to have models of how the FPGA fabric actually evaluates this chip. So what's the model of the time, so you can actually understand the progression of time. But again, for FPGAs, that's fairly well understood, and there's actually tools that will help you extract that information for you. So that's basically the end of my talk. So it's a lot of basically different ways of how we've put time into our language, and going all the way from the Lego Mindstorms all the way up to the Large Collider. Thank you. Any questions?
So we talked about how end users will try to verify. But what about your compiler itself?
That's a good question.
You guys must be worried about it.
We made just a decision that we think there's more. Of course, ideally you want to do both, right? Ideally you want to have a completely validated stack all the way down, but there's other ways to assert that the compiler does the correct thing. Whereas the end users may need may need help actually be able to state the correctness of their programs. In fact, I have a strong belief that just by writing the assertions of their programs, they actually will think more about what they've written and probably eliminate a number of bugs just by writing down those assertions. The next stage is actually not even verifying them, but just running those assertions as part of their program. Third level is actually going through and really verifying it. And then getting even deeper insight into what they wrote and whether or not it actually fits with the specification. Testing, yeah. That's and it's a question of being realistic. The compiler is a very complicated thing, and.
So what about? So you said runtime checking is sort of stage. I mean, when you have purely software, it's kind of already annoying for it to stop something goes wrong. But if you have sort of hardware-centered things, you can't just stop.
No. Well, that depends. It's up to the user to determine what is my error handling here. Is this catastrophic? Should I shut down the system? What should I do at that point?
Yeah, often what you'll have in a safety-critical application is some sort of watchdog that's at a high enough rate looking at what's going on in your system and hearing text things that are unsafe, being able to map from whatever state you're in to a graceful shutdown process.
So I think there's an assertion that dynamic is sort of just keeping extra state information around so that this other agent can sort of query and say, oh, look, things have sort of gone wrong there.
One thing you could imagine. One thing you could imagine is, actually synthesizing assertions into the fabric of the FPGA and having a watchdog process running on the real-time controller that's observing the lines, and when it detects something that's anomalous state, switching into a mode that's shut down that triggers both shutdown logic in the real-time controller and shutdown logic in the FPGA. That's one of the ways you can use it, but I think would be a fairly likely way to use it.
Yeah.
overall system, that when any one of the critical assertions in any substate of execution, like if normal operation occurs, there's a fail-safe out to the non-safe.
But it's already sort of part of the
Yeah.
design.
Yeah.
Like
It has to be.
we're one of the more flexible, open, which also comes as free to opinion yourself as well kind of thing, as opposed to some of the other environments that do this very rigorous control. They've really just gotten down the hatches, and you don't get to violate their model ever.
And you could, probably the spectrum over time, as verification matures, is you might have subsystems that have been verified to within constraints that you feel comfortable with, and you start reducing the amount of watchdog logic you feel is necessary over those systems. I would bet that in practice, people don't immediately say, I verified this and then completely eliminate all watchdog logic.
Right, so it's kind of naive on my side. I wasn't aware that there's already a lot of
There is, yeah.
logic in these systems to make sure that they're in the right
I'd say most of the logic is actually in for the safety critical systems, is in the safety critical
Yeah.
systems, and the actual control itself can often be really simple.
That's right.
It's just you just don't want it to fail.
Yeah, sometimes there's also redundancy as well, where you may have two systems, both doing a system one shadowing the other, and then they both potentially come in and go the safe shutdown mechanism. So there can be layers on top of layers.
A question?
Yeah, so, I mean, it seems like it's pretty cool that you can move a bunch, between a whole bunch of different stacks. But I guess, so one question I have on the formal verification side, especially in safety critical sense, is on timing. I see the flexibility that you get, but what I'm trying to figure out is, for example, what do you consider your basic model computation against which you would verify? And so, going back to the previous question, for example, when you mentioned the variables being asynchronous.
Right.
Like,
So
now I
yeah.
just
So there's a couple of aspects to that. There's the model of computation is independent of timing. Timing is a separate dimension to that you have to add, which is platform specific, because it has to do. There's very different timing when you're running on FPGA, even from one FPGA to another FPGA, but also between the real-time controller and the FPGA. So it's something where the architecture will come up and actually cast a shadow, and you have to bring that into your verification task. These ticks are different depending on the architecture. And will be part of us to model that so you can faithfully verify against it. Otherwise, you can't verify the timing properties.
I would just, to put it in the formalisms of model of computation and those terminologies, I think our basic model of computation is structured data flow, which is basically structured homogeneous data flow, which is, as Jakob said, basically time independent. And then other models of computation that have notions of time, we have to figure out what our formal mapping is. And I think we're not talking about it here, but as related to this issue is essentially, okay, data flow is all about data ordering, and what's absent is time and non-data flow systems. So we're looking at how do we create a model of computation that essentially for us can express asynchronous, heterogeneous data flow, is what I would call it, and prove it correct. And then map both the asynchronous case and the structured case or the homogeneous case to time. And so I don't know if that answered your question or not, but we do see as definitely distinct what we have today and multi-rate asynchronous systems.
So I mean, so one tricky example would be when I asked if you can check the value of time and then make a choice based on that. Right, then you come into the issue of how do you even know that the system is causal?
Yeah, absolutely.
Is it causal depends on
absolutely.
your model of computation, and in some
Sure.
cases undecidable.
No, you're right, absolutely.
And I think we've basically always erred towards what I've found, and I think you can speak to it as well, is when the original creator of Dataflow has been around forever. The novel thing that he came up with was essentially the structures for program flow control, which then made it useful for a broader set of problems, but also introduced a huge amount of non-correctness in terms of formally proving things. So if you leave yourself narrowly constrained to what's formally provable with the existing set of models of computation, in my opinion, you wind up solving not very many problems. And so you have to pragmatically balance how many problems can I solve but leave myself open to non-formalism versus formally being correct and solving very few problems. And so we're trying to strike a balance, and I think the very point you made is we'll probably come up with really good representations of asynchronous systems, time-based systems, and what we have, and there'll be little corners where you go over there, we're not going to be formally correct. Or provably correct. It may be functionally correct.
One of the things we tend to do to supplement to make that realistic for our customers is target and you start using elements of the language that go beyond it, you can simply tell you this is something we can't reason about yet. And that's a way to sort of introduce, growing technology stack over time that let you get some useful work done for a part of your system right away.
This is a little off topic, but like, how, you're talking about passing timestamps. And you've got a plant that's got lots of pieces that have been by different subcontractors. How do you know what timestamp, what the time is?
Well, that's a good question. So this is where some of the depends on the infrastructure, but this is where some of these synchronization technologies like 1588 and DPS synchronization basically can inject the correct notion of time, so everybody has a common notion of time. Because if you don't have that, that goes all the way back to the power plant distribution example I showed right in the beginning. If these things are not correlated, you can't make sense of it. You can't do any analysis on it. These are just graphs, and they show something, but you can't, if you don't have that common sense, and that's exactly the sense here. So this is where something like 1588 is a very powerful technology that allows you to distribute a very precise clock in your system.
So what if you don't have control? I mean, in these systems, platform systems, you tend to have complete control over everything to a certain degree.
Right.
What if you're out in the real world? That's real, and you've got, for instance, RFID type smart device systems, and you don't have a standard timing wire or some standard way of talking about time. How do you handle that?
Well, I mean, so the best approximation is you timestamp it when you can, using a common time. So that once it gets into the perimeter of where you know where your common time base is, you start timestamping it. Or you purely just basically, when you see it, that's when you think that's the timestamp you have. It's not very good, but it's limited by that. I mean, there's.
You can solve it. To be fair, though, it's not very good, and it solves a lot of problems. Like back to, if I look at 1588 and what it solves, it's really good at having Jakob and I coordinate our watches and go, okay, we're on the same time now. Now we're going to act accordingly. So at 2 o'clock, we'll both do the same thing, and so we'll have a synchronization moment. With industrial automation systems that basically build stuff, beer, ice cream, whatever, they timestamp, very coarse-grained, uncorrelated, more or less. I'm going to make my best approximation of what the current wall clock time is, that's globally accepted time. That'll propagate as a data value somewhere, and they'll all go, look, it all happened close enough. Yeah. And as long as the process itself is slow, that's accurate enough.
It all depends. It all depends on the time scale you're looking at. Yeah.
If you want to run on some device that's so low powered in its computational capability that it can't possibly run a 1588 stack or a GPS stack or anything like that, then what you're going to have to do is introduce into your hierarchy something that can translate very basic tick count type information from these ultra low power devices and map them into a more standard world in some fashion.
Thank you very much.
GPS stack, right?
That would be one way. Take RFID and translate it into the GPS world, or you can take RFID and find a way to translate it into the 1588 world.
Okay. Thank you very much.
Thank you.